Hello, this is the Anova PowerPoint presentation. And I'm also going to go over, experimental and control groups briefly. So Anova is kind of like a t-test. And it's a statistical test designed to examine the means across more than two groups of subjects. It is based upon variability. This is variance for the mean. We went over there first week. These ratios of variance are used to determine if there are differences in the groups. And the variability in statistics is how spread out your points are. Okay, so this is commonly referred to as variability or dispersion. There are no limits to the number of groups you can test. Under ANOVA, the null hypothesis, in other words, the lack of a hypothesis, where the invalid hypothesis, is that everything is equal. And then generally, the hypothesis is that at least one group, the alt hypothesis, I should say, is that one group is different than the rest. When scores are divided into three groups of variations, can be divided into two parts. The variation of scores within the groups, think standard deviation, and the variation of score between the groups, which is how scores vary from one group to the next. ANOVA compared these two types of variance. So the heart of ANOVA is whether the between groups is significantly larger than the within groups. The statistical procedure in the ANOVA is called your F-test, and your F-test shows that ratio of the two estimates of variability, your within groups and your between groups. And if the null hypothesis is true, then the variation between the groups should be similar. So if your null is false, then you should see the differences. And I want you to remember that ANOVA always tests null as no difference between all the groups. And I'll show you. So if the F-test is statistically significant, then you can reject null. If the null hypothesis is true, you can expect F to have a value close to 1. And a large F ratio, 5.14, means that the variation among the group is no more than you'd expect to see by chance. ANOVA requires that you have a random sample from a larger population. Remember that a population is everything. In other words, they'll take the entire University of Louisville. That's a population. Now, a sample would be if we just take 100 students from the University of Louisville and ask them questions. That would be a sample. It had to be randomly selected amongst all departments. The single dependent variable must be measured at interval ratio level. Interval ratio just means it is a number. It's an actual number like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 that has a rank value between them. 1 is bigger than 2. 1 is smaller than 2. 2 is smaller than 3, and so on and so forth. The independent variable needs to only be nominal, ordinal, so categorical, eye color, blue, green, for example, or ordinal. It's actually a rank ordering, but still, kind of a word category. Poor, middle class, upper class kind of deal. Recall, you can downgrade, but you cannot upgrade, so you cannot convert your interval ratio to ordinal or nominal. And here's some way to convert when you do need to convert. So if you have a data set with crime rates that range from 0 to 100, you can organize these and put them into categories. 0 equals 0, 1 equals 1 through 25, 2 equals 26 through 50, 3 equals 51 through, let me get my pen out here. 3 equals 51 through 75, and 4 equals 76 through 100. Now recall here that we have a range of 0 to 100, okay? So we do have 100 present and 0 present, meaning these choices exhaust everything, okay? They exhaust everything. Everything is present. There's nothing missing. They also do not overlap, and this is crucial that your categories do not overlap. Notice that we go 1 through 25, and then we start at 26. We don't start at 25 because that will make them overlap. 50, and then we start at 51, into 75, and we start at 76 for the next one. So using this, we can label 0 as no crime. 1 represents little crime. 2 represents moderate crime. 3 represents major crime. And 4 equals severe crime. You can watch this YouTube video for calculating ANOVA in Excel. It is there for you if you need it. So go ahead and take a look at that. In the meantime, I'm going to show you experimental control groups. I'm also going to show you, oops, I didn't mean to keep that. Well, it is what it is now. So let's make a new Excel sheet here. New Excel sheet. So, all right. Let's say we have experimental. We'll say we'll have 2 experimental groups, okay? Experimental 1, experimental 2, and control. We're going to rename these. So we have 3 groups. 3 groups. Now, we'll say that we have 10 people, and we gave each of these people a different medicine, except for the control group, which received no medicine. Okay, they just had a cold. We'll use cold duration from the slides, right? From the slides. Okay, so 10 people, and the question, the research question is, which cold medicine works best? Okay, data is how long the person was sick. Okay, pretty simple stuff. So for experimental 1, we'll use Tylenol, cold, and flu. In experimental 2, we'll use NyQuil. Okay, and then in the control group, excuse me, the control group just roughed it out. Okay, nothing was given to them. Actually, in true fashion, we'll say sugar pill. But they still had to rough it out. But they didn't know they were roughing it out. Okay, so we got 10 samples, so we're going to put down 10 points of data. So let's say this person stayed sick for 5 days. This person stayed sick for 6 days. We got a 3-day sicker. 5, 6, 7, 7. This one stayed sick way longer than they should have. 8, 5, and 6. That's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We got sample size 10. And then NyQuil will go with 5, 5, 4, 2, 3, 5, 6, 5, 5, 3. And then control pill, the sugar pill, let's say they were sick for 8 days, 9 days, 8 days, 7 days, 9 days, 6 days, 9 days. We'll have even a 10-day for this one. 8 days and then 7 days. This will be our data. Okay? So this is our control group. I'll highlight control groups in yellow. Oops. That would be the print. So our control group is yellow. And then we will highlight our experimental groups in this little teal color. Okay, so experimental, which is medicine intervention. Okay, and our control pill. So our hypothesis will be cold medicines reduce the duration of the cold. Okay, simple. In other words, our dependent variable is the duration of the cold. Okay, that's the dependent variable. How long the cold lasted. And our independent variable is cold medicine, or, in this case, the sugar pill counts as a cold medicine, okay? Let's make it really even more vaguer, okay? We'll say cold medicines have an impact on the duration of, colds. Of a cold. Okay? Simple. Simple, simple, simple. So let's go ahead and lay out our Anova in this case. And let's go ahead and go to data and data analysis. We're going to go Anova, two-factor without replication. What we're going to do here is we're going to go highlight this thing right here. We're going to highlight everything. We're going to include our labels. And we're going to hit OK. And this will present an Anova. Okay. So let's go ahead and make this bigger. This is what we're interested in. This is just showing the summary here. Okay. So no, this is Excel. So use your control group first. Let's try this again, so it's less confusing. Let's go ahead and delete this. All right, now data analysis, Anova, two-factor. We're going to do the same thing. There we go. So control groups first. All right. Let's take a look. So, all right. So for our rows, in other words, our between groups, we got a p-value of 0.06. And for our columns, or in other words, our groups itself, this, we actually do see a difference. Our 0.006, which is we reject null for that. We do reject null for this. Let's go home. Let me highlight this. Meaning that indeed, if you're given a cold medicine, it reduces your duration of cold. Now let's take a look at this. Okay. Experimental 1, Tylenol. The cold on average lasted 5.8 days. For experimental 2, the cold on average lasted 4.3 days. Both, shorter than, the control group. Now let's go ahead and include our control group. With the single factor test. And you can see here, this is significant, by the way. Okay, so Anova's single factor, I'm going to say this real quick, is what you want to do for an experiment like this. And you can see quickly between the averages here, your control group, which is sugar pill, the average cold lasted 8.3 days. Tylenol lasted 5.8 days, and NyQuil lasted 4.3 days, meaning, NyQuil was more effective in getting rid of the cold faster. And we have a p-value of 6.7521 e to the -7. Now, what does that mean? Well, that's a very small number. What this number actually is, it's around this. It's around this right here. Okay, I'm not going to exactly count it, but when you see that negative, the e negative whatever, you can see right here. You can see it again. It actually is beautiful Excel that it does that. It converts it straight off. So that's what the number actually is, right here. Okay, so your p-value is 0.00006721, which is much smaller than 0.05, which means you reject null. In other words, this is pretty good. NyQuil is scientifically effective in reducing that cold, and you could even say by 4 days. If you take NyQuil, your cold will last 4 days less on average than if you don't take anything. Going even further, you can say if you take NyQuil, then you can expect to get over the cold a day and a half faster. So that's how that works, and that's how Anova works. So next is crosstabs and chi-square, and join me in the next video.